Okay, I hope everybody is having a good day today. Today is the second part of week 7, and what we're going to be doing today is a review of trigonometry. How many of you have had any trig at all? Show of hands. Okay, so for those of you that have had trig in the past, do you feel comfortable with it? I mean, have you used it in the last couple of years? Okay, so we're getting no's on that. And those of you that are taking the distance course, I'm sure fall into the same category. Some of you have more experience with trig, some less. Some actually may be in a trig class right now, in which case this is probably not even something you need to watch. But if it's been a while since you've had trig, what I'm going to do is I'm going to show you a technique toward dealing with trigonometry that will work for about 80 to 90% of the problems that you will do. And that's even if you go on to get your 4-year degree in engineering and even beyond that. Okay? Now there's an acronym that we use in the study of trigonometry that you usually don't get to until about the 4th week or so of a formal trig class. But we're going to condense all that into this lecture today. And that acronym that we use is SOH CAH TOA. And the way I like to think of it is sort of like if I drop something on my foot, right? My foot would be hurting, and I would want to go home, and I'd want to soak my toe in Epsom salt, right? So I just think, oh, I dropped something on my foot, I'm going to soak my toe. SOH CAH TOA, okay? But it's really not grammatically correct, because when you see the way that the acronym is written, it really reads phonically SOH CAH TOA. Okay? So the acronym goes like this. SOH, so, and then a space, CAH, CAH, SOH CAH TOA, TOA, SOH CAH TOA. Okay? Now, the reason that that's useful is because what it does is it gives you a tool to memorize the primary trigonometric functions all in one little thing, SOH CAH TOA. And I'll show you what that is. The sine of an angle is the opposite over the hypotenuse. The cosine of an angle is the adjacent over the hypotenuse. The tangent of an angle is the opposite over the adjacent. Now, even that may not mean that much to you, but once I get done with this exercise, it will. Okay? The other thing that's nice about this little acronym SOH CAH TOA is that it will help you to determine which function in trigonometry you need to use in order to solve for your problem. In other words, are you going to use the sine function, the cosine function, or the tangent function? Okay? Now, a lot of you, as I'm going through this exercise, teaching you how to use trigonometry, may ask questions like, what really is this? Okay, well, what this really isn't right now is a lecture on formal trigonometry in mathematics. This is a lecture on how to use trigonometry in electrical engineering technology to solve for circuit parameters. Okay? Big difference. Example. This very first part of the acronym, SOH. This stands for the sine, written as SIN or sin. The sine of an angle theta is equal to the length of the side opposite divided by the length of the hypotenuse. And again, we're talking about a right triangle. Okay? So if this is an angle theta right here, and you think of your eyeball as being down here in this corner right here, if you look straight out from the corner, this is the opposite side. If this is the opposite side, this must be the adjacent side. The longest part of the triangle is always called what? The hypotenuse. Okay? So the sine of the angle theta is equal to the ratio of the length of the opposite side, 3 inches, 4 inches, whatever it is, divided by the length of the hypotenuse, 7 inches, 9 inches, whatever it is. Now, a lot of people will ask, but what is this right here? Sine. What is this? Now, if I was teaching a traditional trigonometry course, I would have a very different answer for you than I do in this class, because we just don't have enough time to spend the rest of the semester studying trigonometry. And so what I'll say to you, if you ask me the question, what is this right here? My response to you is, it's a button on your calculator. Okay? Okay, what we're going to do is we're going to use that button on your calculator in combination with ratios of lengths of sides of a triangle to calculate angles. And your calculator is going to do most of the work. You're just going to have to know how to push the right buttons. Okay? For the second part of SOH CAH TOA, we define the cosine of the angle theta. And that's equal to the length of the side adjacent the angle. So the length of the side adjacent the angle divided by the hypotenuse of the angle. And then finally, SOH CAH TOA. For TOA, that defines the function tangent. The tangent of the angle theta is equal to the length of the side opposite the angle divided by the length adjacent the angle. So do you see how that acronym right there allowed me to memorize these formulas? I honestly do not have these formulas memorized. The way that I generate these formulas is with stubbing my toe, thinking about SOH CAH TOA. Okay? Now, let's look at a couple of examples of how this is actually used. Because it turns out that we usually don't use the trigonometric functions of sine, cosine, and tangent in this form. Why? The reason is because we're usually using these functions, which are, again, buttons on our calculator, to find the angles that are inside triangles. And the triangles represent voltages, currents, powers, resistances, impedances, things in AC circuits. Okay? So if we're trying to figure out what the actual angle is, because you notice here that this says that the sine of the angle is this ratio. It doesn't say the angle is this ratio. It says the sine of the angle is this ratio. Okay? The angle itself, theta, is equal to the inverse sine, also known as the arc sine, of that same ratio, opposite over hypotenuse. This right here, another button on your calculator. So usually, if you look at your calculator right now, and let me grab one, we can probably, this is a TI 86, but any of the TIs, where my thumb is right here is just below the sine function. And so if you look just above the button here that I just pushed and moved my thumb down below, you'll see the inverse of that function, also known as the arc sine. And then if I move to the right, there's the cosine, and then the yellow is the arc cosine, or the inverse cosine. And then if I move one more to the right, there's the tangent, or the arc tangent. Okay? So those buttons right there, in conjunction with the ratios of the lengths of the sides of the triangle, will allow you to figure out the angles that are inside. You get enough of that? The angles that are inside the triangles. Now, let's finish this by figuring out what the angle is using the cosine function. The angle using the cosine function is the inverse cosine of the same thing, the adjacent over the hypotenuse. Up here, adjacent over hypotenuse. So it's the ratio of the length of the side adjacent over the length of the hypotenuse. And then finally, if you want to find the angle theta using the function tangent, which again is a button on your calculator, then theta would be equal to the inverse tangent, or the arc tangent, of the opposite over the adjacent. Tangent is opposite over adjacent. So it's the length at opposite divided by the length adjacent. Those formulas should be written down on your reference sheet, okay? Because those formulas are going to allow you to figure out any length of the side of a right triangle or any angle within the triangle itself. So let's take a look at an example. This is what I'm giving you. And this is your check for understanding. This is a right triangle. Here is your 90-degree angle right there. Okay? This right here is 19.7. 19.7 feet. And this right here, the horizontal component, is 12.2 feet. I want to know what this angle phi is right there. I want to know what the angle is between the hypotenuse and the vertical component of the triangle. So we'll give just a couple of moments for those of you that are watching it to work on it, see if you can figure it out, and then I'll set the problem up. Remember that you need to pay attention to where your opposite and adjacent sides are. One hint is that your opposite and adjacent sides have just switched, because I'm asking for the angle phi, not theta. Okay? All right. While you're still working on it, I'll show you exactly how I would approach this problem if I came to it dry. I would write down my acronym. SOH CAH TOA. SOH CAH TOA. SOH CAH TOA. And this is an A. Okay? Now, the next thing that I'm going to do is I'm going to come over here and I'm going to ask myself, what is it that I'm looking for? I'm looking for this angle right here between the hypotenuse and the vertical component of this right triangle. So if I imagine my eyeball being in this corner right here, then my opposite side would be right over here. So this is the opposite side. This is my opposite side right here. If this is my opposite side, then this has to be my adjacent side. And then obviously the longest part has to be the hypotenuse of the triangle. Now what I'm going to do is I'm going to use this to go and figure out which function I'm going to use. I have the opposite, I have the hypotenuse, I do not have the adjacent. So I don't want to use any functions that require me to know the adjacent length. Well, let's go look for functions that require adjacent lengths. How about if I come over to TOA? That requires adjacent length. Not going to use that one. How about CAH? That requires adjacent length. Not going to use that one. Sine. Oh, this one is opposite over hypotenuse. And guess what? I know the opposite and I know the hypotenuse. So I'm going to use the inverse sine. So phi is going to be equal to the inverse sine of the ratio of the side opposite divided by the hypotenuse. And that's simply going to be equal to the arc sine of 12.2 divided by 19.7. And what are you getting for that? What is it? 38.26 degrees. Anybody else get that? Okay. How did you do it? Oh, I see. So you, oh, okay. But would you agree that this would be the least amount of work? So there are a lot of different ways to do it. Like you could use the Pythagorean theorem to calculate this right here. Then you would be able to use either this one or this one or this one. Okay? Now you might ask, where does all of this come in? Where does all of this come in? And what I'm going to do is I'm going to show you what the sine function looks like when we plot it on an oscilloscope, or what's known as the time domain. If we have a plot of time versus voltage, time versus voltage, this is what a sine wave looks like. Okay? If the black represents, let's say that we have a circuit. And in the circuit, there is an AC function that's driving the circuit. That could be like Diablo nuclear power plant. And we hook up to that AC circuit a resistor and a coil of wire, which is also called an inductor. It's called an iron core inductor. It is going to turn out that if the black represents voltage, and then we plot the voltage and also the current is going to look like this. And the thing that's noteworthy about this is that they don't pass through zero at the same time. This right here represents a phase angle. A phase angle or a phase delay. It's actually a delay. okay? And it all gets into the acronym Eli the Iceman, which we won't talk about tonight. But solving these triangles refers directly to AC circuits and the phase displacement between voltage and current on an oscilloscope. Okay, so it's very applicable and very useful, and something that you're going to have well mastered in order to be able to do the problems. But again, the purpose for this lecture was just to review the trigonometry, okay? Not to teach you everything else in AC, because that's what the rest of the semester's for. Any questions about SOH CAH TOA? Sir? Right, okay.
What is the ideal? Is to have the current and voltage?
The ideal is to have the current and voltage in phase with each other.
Exactly.
In which case they would cross through zero at the exact same moment. Right. And that's what you have in a purely resistive circuit.
So the more delay between the voltage and the current, the worse the power factor.
The worse the power factor, yes. You need, but you're getting into things that others aren't ready for yet. Yeah, that's about 5 weeks from now, power factor. Okay? Other questions? That was a good question. The question was, does this have something to do with a phenomenon that we study in electrical engineering called power factor, which is directly related to efficiency? And the answer is yes. As a matter of fact, just to close out, the power factor will remain unknown. The power factor of any circuit is equal to the cosine of the phase angle. So when you go and you find this phase angle right here, if you take the cosine of it, that will tell you how efficient your circuit is. Okay? I think we've pretty much run out of time. Great question. If you have anything else, feel free to come up and talk to me afterwards. Otherwise, have a safe drive. Good night.